Set theory defines infinity as a strictly organized hierarchy of cardinalities. We prove some infinities are objectively larger than others by comparing real numbers to the counting numbers. Georg Cantor proved that the infinite set of real numbers is strictly larger than the natural numbers, breaking the intuition that all infinite collections must be equal in size. To compare infinite sets, we use cardinality. Two sets have the same size if a one-to-one correspondence, or bijection, can be established between every element of both sets. Natural numbers serve as our baseline for countability. We denote the cardinality of this infinite set using the Hebrew letter aleph with the subscript 0, pronounced aleph null.
Any set that can be perfectly paired with natural numbers is countably infinite. This includes sets that seem larger, such as the set of all integers or all even numbers. Surprisingly, the set of all rational numbers is also countably infinite. Even though fractions are dense between any two integers, they can still be ordered into a single exhaustive list. Cantor demonstrated this by arranging all positive fractions into a two-dimensional grid and traversing it in a diagonal zigzag pattern. This ensures every rational number eventually receives a unique position.
This mapping establishes that increasing the density of points does not necessarily increase the cardinality of an infinite set. All common infinite sets seem the same size until reals are considered. Now we examine the set of real numbers located in the unit interval between 0 and 1. This includes rational fractions and irrational numbers like the square root of 2 minus 1. Every real number in this interval is represented as an infinite decimal expansion. 1/3 is 0.3 repeating, while irrational numbers have non-repeating digits extending forever to infinity.
To prove reals are more numerous, we use a proof by contradiction. We start by assuming the opposite, that the set of all real numbers between 0 and 1 is countably infinite. If the reals were countable, a complete list would exist containing every real number. We label these as x sub 1, x sub 2, x sub 3, and so on, indexed by the set of natural numbers. Visualize this list as a vertical column, where each row is a real number. Each number is written digit by digit across the horizontal axis, creating an infinite matrix of numerical data. The first number might be 0.1415. The second might be 0.5000, and the third might be 0.7826. Our goal is to construct a new real number, which we will call d, that is definitely not in our list. If we succeed, our assumption that the list was complete is false. We construct d by examining the diagonal digits of our matrix. We isolate the first digit of the first number, the second digit of the second, and the nth digit of the nth. The construction rule for d is simple. We define the nth decimal digit of d to be intentionally different from the nth decimal digit of the nth number in our supposedly complete list. To avoid complications with repeating decimals, like 0.49 repeating equaling 0.5, we restrict our choice of digits for d to values like 4 and 5 only. This rule of digit mutation ensures that our new number d cannot be equal to any number already present in the list. It differs from every listed number by at least one digit. Let us trace the first digit. Since the first digit of d is chosen to be different from the first digit of x1, d cannot equal x1 regardless of its other digits. Now we check the second digit. Since the second digit of d is different from the second digit of x2, d cannot equal x2. We have differentiated d from the second item. This logic extends to any natural number n. Because the nth digit of d is purposely changed, it can never match the number indexed at position n. Every row is bypassed entirely. The result is a valid real number d between 0 and 1 that is absent from our mapping. No matter how we arrange the list, we can always find a missing number. This proves that a one-to-one correspondence between natural numbers and real numbers is impossible.
The cardinality of the reals is strictly and demonstrably greater than the cardinality of the counting numbers. We call this higher level of infinity the power of the continuum. It is denoted by the lowercase letter c, or by the expression 2 raised to the power of Aleph null.
Cantor's diagonal argument reveals that infinity is not a single destination, but a landscape of varying magnitudes. This was a radical shift in mathematical and philosophical thought during the late 19th century. The argument generalizes to any set. Cantor proved that for any set S, the set of all its subsets, known as the power set, always has a strictly larger cardinality than S. This leads to an endless sequence of increasingly large infinities. We can take the power set of the reals, then the power set of that result, climbing higher into the transfinite realm. A famous question arising from this is the continuum hypothesis. It asks whether there exists any infinity that is larger than the natural numbers but smaller than the set of real numbers. In 1940, Goedel showed that the continuum hypothesis cannot be disproved using the standard axioms of set theory. This proved that the hypothesis is consistent with our mathematical foundation. In 1963, Paul Cohen proved that the continuum hypothesis is independent of standard set theory. This means the existence of an intermediate infinity can neither be proven nor disproven within our framework. The diagonal method is more than a curiosity. It is a fundamental tool in mathematical logic. It allows researchers to prove precisely what can and cannot be achieved within formal systems. Alan Turing adapted the diagonal argument to prove the undecidability of the halting problem. He demonstrated that no general algorithm can determine if any given computer program will eventually stop or run forever. If such an algorithm existed, one could construct a diagonal contradiction by creating a program that intentionally does the opposite of what the halting algorithm predicts. This logic destroys the possibility of the algorithm. Similarly, Goedel used a form of diagonalization to prove his incompleteness theorems. He demonstrated that any consistent formal system capable of arithmetic contains true statements that cannot be proven within that system. Diagonalization helps us map the absolute boundaries of logic and computation. It confirms that the space of possible mathematical truths is far vaster than the set of truths reachable through formal proof. In computer science, this distinction is vital for identifying problems that are solvable in theory versus those that are fundamentally uncomputable. We use it to classify the complexity of algorithms and data structures. The fact that there are more real numbers than counting numbers has deep implications for physics and measure theory. It defines how we calculate probabilities and lengths in the continuous space of our universe. Cantor's work faced intense resistance initially, but it now forms the bedrock of modern mathematics. It transformed our understanding of the infinite from a vague mystery into a rigorous and measurable mathematical quantity. Mastering the diagonal argument provides a precise instrument for navigating the infinite hierarchy of mathematical reality. It remains one of the most elegant and profound proofs in formal reasoning, defining the modern understanding of the transfinite.